What I'm going to do today is go through a history and design of ion exchange columns, really focusing on anion and cation IC columns. It is certainly not the full extent of things that I've worked on. And really everything I'm going to show you today is also in can you go to the next slide, Alexandra? Is in this book that we published, I think it was in 2021 is when it was finally published. And thanks to the COVID lockdown, I managed to finish that chapter during the time when I was in lockdown. Anyway, if you're interested in more details, every one of the slides I show today is also has a section associated with it that has more details than I'm going to be able to go into today, because it's like about a 90-page chapter or something like that. And it goes into other phases like ion exclusion phases and things like that I'm not going to discuss today. So how about go to the next slide, please? So I'm going to start with columns. They're in order of introduction, but not necessarily in an order of technology. And that in terms of the column technology, I'm going to jump around a little bit because I've grouped them by eluent type. But anyway, if we could go to the next slide. This is a chromatogram of a column at the time when I joined Ionics in 1979. You can't really read that very well, but that chromatogram is from 1980, so it was a little after I started. But at the time when I was working there, when I first started, the columns we were using were packed in glass tubes. And they were like 25-ish micron particle size. You can see the efficiency isn't very good because I think that's like a 25-minute run or something like that, if I remember right. And even so, you didn't really have baseline separation of bromide and nitrate on this early phase. Go to the next slide, please. So this is the big jump forward, but it's, based on the same technology shown in that previous slide, in the sense that it's using non-porous resin that's been surface sulfonated, but instead of 25 micron particles, I think these are around 11 micron particles. And we made a number of changes in the stationary phase in order to optimize the selectivity. Obviously, we can separate columns like that, like the AS4ASC. You can separate the common anions in 8 minutes with no problem. And, this SC nomenclature we added at one point in the development of the columns to indicate that it was solvent compatible, in case you're wondering what that stands for. Because the earlier version of AS4A was used 4% cross-link resin. The column I showed you previously used 2% cross-link resin, which means it's really not compatible with solvent. Even 10% solvent will usually damage the bed because it will swell too much in the solvent. But the AS4ASC and really most of the columns developed around that time and after use 55% cross-link resin, which swells only a very small amount in organic solvents, as is the case with this column. Next slide, please. So this is a column I'm betting most people in the audience never saw, or maybe didn't know it ever existed, but we this is one of the earliest columns we developed using acrylate-based stationary phases. The previous chromatogram with AS4ASC uses a styrenic monomer, vinyl benzyl chloride. But here, taking advantage of the selectivity of methacrylate ion exchange materials, we were able to separate the common anions in just a little bit under 2 minutes. I think, if you want to know why you can't still buy this column, I think it's mainly because, to get that kind of resolution, you have to have really very low dead volume in your system. And a lot of customers at the time when we introduced it had too much dead volume to see that kind of a separation when they put it on their system. So what it turned out, it wasn't very popular, even though the separation is pretty fast, and it actually shows one thing that's a misnomer in chromatography. This particular column used, I think it was 15 micron resin. So obviously you don't need small particle size to do fast analysis. You just need the right selectivity in order to separate 7 anions in 2 minutes. Of course, I should say that's a 3 mil per minute separation, which probably most people wouldn't be interested in today. Next slide, please. Now this slide kind of shows the other side of the acrylate-based chemistry platform. The AS9SC was really the first column. Of course, it wasn't the SC version, but the AS9 was the first column we developed using the acrylate chemistry. And we started using it because it had better selectivity for bromide, chlorate, and nitrate, 6, 7, and 8. In comparison to styrenic monomers, typically chlorate has a little longer retention time. So once I realized that you could get better selectivity with methacrylate polymers, I went about optimizing a chemistry for that separation. And late in the development, we were contacted by the EPA. They wanted to know if we had a column for separating bromate, and it turned out the column had a baseline separation of bromate from chloride, which was, again, not what was normal with the columns at the time. So the column kind of became more of a bromate column than a chlorate column in the early days. But one of the problems with it is that if you're trying to do bromate analysis, you need higher capacity because you're typically injecting a pretty large volume in order to deal with the low detection limits of bromate in environmental samples. So we later developed the AS9HC, and as you probably know, the HC means high capacity. So the idea was, it's a higher capacity version of the AS9, but in many cases, like for the AS11, which I'll talk about in a minute, the chemistry is almost identical between the non-HC and the HC version. But in this case, we made some other changes. We developed a monomer that's more pH stable than glycidyl methacrylate that we used on the AS9HC, so that you could use just carbonate as the eluent. And using a higher ionic strength eluent has the advantage that you can the loading capacity of a chromatographic system is a function of both the concentration of the eluent and the capacity of the column. So having a column that works with more concentrated eluent has the advantage of helping to boost the dynamic capacity of the system. And as you can see, we also juggled the selectivity a little bit so that the spacing was more uniform on the AS98C. Next slide, please. Alexandra, can you switch slides?
I did. This is AS12A showing
sorry.
right now.
Okay, now it is. All right, I guess I wasn't paying attention. All right, so the AS12A was a response to our first response to the introduction of the Sericep AN1 column from what was then Sericep, which later became part of transgenomic and is now part of concise separations, I think. But anyway, that column was the first column really that gave a baseline separation of fluoride from the injection void, and so we embarked on a program. Our team in Japan was having trouble in Japan because of the competition from this column. And they actually wanted to OEM the Sericep column, and we said we would develop a column that was, an in-house column. And so we had an intense R&D effort led by several chemists. There were actually two projects in parallel, but this was the product developed by Charanjit Sani. And it uses what we call a super macroporous resin. It's a resin substrate that's nominally around 1,000 angstrom, but it depends it's somewhere between 1,000 and 1,500 angstrom pore size. And the reason for using a large pore size is that this phase is coated, it's surface sulfonated and then coated on the inside and the outside surface with latex. And doing that, even though it constrains the size of the latex, allows you to get about 5 to 8 times higher capacity than you could get from a non-porous resin with latex on the surface. And we needed that in this case because in order to get the good separation of fluoride from the void, we need really low crosslink, and low crosslink means the particles swell a lot. And so we're using, very low crosslink latex to achieve this separation. And you can see that the fluoride is resolved from the void. There are a couple of interesting things about this column that you might not have noticed. One of them is, well, it's not hydroxide selective at all, and I'll talk more about that in a bit. But the other thing is most columns, the fluoride peak elutes either after or very close to chloride. But in this column, it elutes between chloride and fluoride. So you might notice a vacancy peak there. But if you happen to have a sample with a high ionic strength, often that vacancy peak interferes or causes peak splitting for chloride, and you don't really see that on this column because of its location. Of course, if you're trying to do organic acids in the gap between chloride and fluoride, that can be a problem. But anyway, so that's an interesting thing about this column. And you notice that at low crosslinks, chlorate is resolved from bromide and nitrate, even though we're using an aromatic monomer here. Next slide, please. All right, so now this slide, that, got us, achieved the objective we had, but we continued to have people saying the Ceresep AN1 column was better. And so we kept on working on making even higher water content phases. We'll talk a little bit later about the first use of grafting. It was in the CS12 column, at least for us, but here you see an AS14 column, which is a grafted anion exchange phase, and this was the first anion exchange column we made using grafting. The advantage of grafting is it has no crosslink. It's just polymer chains attached on one end to the surface, but because it has no crosslink, you need a fairly high surface area. So here we're using resin with a pore size of around 80 to 100 angstroms and a surface area in the range of around 450 square meters per gram. So we have enough surface to provide the necessary capacity, but because there's no crossing, you can see the void separation of fluoride is even better. And we also have better separation of acetate than we did on the CS12A. Next slide, please. And then, we continued that effort to develop the AS14A, which is a grafted anion exchanger where the monomers are aromatic, so they were more stable than the AS14 was in terms of pH stability. And you can see the resolution of fluoride from the void is even a little better than the AS14. And peak shape for things like nitrate is actually better as well, even though normally peak shape is better on acrylates than aromatic monomers, but because of the monomer we used is more hydrophilic than VBC, so we got better peak shape as well for this column. Next slide, please. So then, well, I'll talk more about the chemistry behind it on when I get to the hydroxide columns. In the early 2000s, because we needed a pH stable phase that would get good resolution of bromate from chloride with a hydroxide eluent, we developed a technology called electrostatic attached hyperbranched condensation polymers, where we're using the same wide pore substrate I described for the CS12A, but here we're making a hyperbranched film that has no aromatic structure whatsoever. This is all ether or carbon bonds in the network or ion exchange sites at the branch points. And as you can see, that gives you a couple of advantages. One is a better peak shape than with a grafted material, especially near the base of the peak, but also, a pretty decent resolution of fluoride from the void, depending on how you make the material. Here in the AS22, you can see the column was optimized to be similar to the runtime of an AS14. Next slide, please. And then here with the AS23, you see the version optimized for use with carbonate eluent that gives a nice separation of the oxyhalides as well as the common anions. And here again, we opted for a more concentrated eluent than we would normally use with earlier columns because the capacity is significantly higher. I think next slide, please. Now let's jump into hydroxide columns. As you probably know, hydroxide columns are kind of the mainstay of ion chromatography when it comes to anions. While we have continued to make new columns for carbonate, here's an interesting comparison I did during the time of the development of the AS11, which I'll talk about in a minute. But here you see the importance of understanding hydroxide selectivity. So if you look at the AS4 column is a phase that had a quaternary nitrogen with only aliphatic R groups. The AS4A has one beta hydroxyl group near the quaternary ion exchange site. The AS5 has two, and the AS5A also has two beta hydroxy groups, but the crosslink is higher with the AS5A than the AS5. But you also notice that the peak shape for bromide is not as good as some of those columns you just saw, like the hyperbranch ones. But anyway, the point is that you observe that hydroxide is more efficient at eluting ions if you use if you add more beta hydroxyl groups to the quaternary ion exchange site. And that's because those hydroxyl groups are weakly acidic, and there's an inductive effect from the quaternary site that makes them more acidic than they would otherwise be. So they have a pKa that's around 12. And that means in a highly hydroxide rich stationary phase, they can be in equilibrium with a zwitterionic state where you have a quaternary ion exchange site and an ionized hydroxyl group. And that's what gives hydroxide more elution power than it otherwise would have on a aliphatic phase. Next slide, please. Now, this was the first, Sandy Dasgupta had published, I don't remember exactly when it was, but in the 80s, that doing gradient separations using ion pair chromatography and a suppressor. And so that motivated us to try to design, around the same time we had just developed what became known as the micromembrane, the MMS, micromembrane suppressor, which had much higher suppression capacity. So we designed this column, the AS5A was the first column we designed specifically for hydroxide gradients. And you notice, if you're familiar with newer columns, that many of the anions in this separation are the same as you see in later columns. But if you look at the eluent concentration, you'll notice that if you work out that 85% of E1, which is 200 millimolar, means that's 170 millimolar hydroxide. So we still don't, you could say we still don't really have enough hydroxide selectivity to make hydroxide gradients really practical, but at least, if you're willing to live with using such high concentrations, we could do a pretty decent separation of organic acids. Next slide, please. Now, this column, the AS10, which is another one that is not very popular anymore, so maybe many of you might not have ever used it, was the first column. It's the reason why we developed the super macroporous resin in the first place. Now, the idea was to make a hydroxide eluent column that would give, a good isocratic separation of common anions with fluoride well separated from the void, based on the fact that the separation of hydroxide, a monovalent species relative to divalent species is partially a function of the phase, but partially it's a function of the eluent concentration. So at higher concentrations, the monovalents and the divalents have more similar selectivity. So we basically developed this phase to provide high enough capacity so we could use a pretty concentrated eluent and still have a decent retention of weakly retained ions like acetate or formate that you see here, as well as having good separate a relatively short retention time for sulfate, for example. All right, next slide, please. Now, around the same time, we had a consulting arrangement with Professor Hatch at New Mexico Tech, and there he suggested, I was bemoaning the fact that when we tried to make ion exchange sites with 4 hydroxyl groups, with VBC as a monomer, the only option is to use triethanolamine, and that doesn't, it's really not, steric hindrance makes it difficult to get that reaction to go, and you get a lot of cross-linking side reactions. So he suggested we should make an epoxy monomer. And so based on his suggestion, the synthetic chemists in our group synthesized an epoxy styrene monomer that we used first to make the AS11HC, but then after that, almost all of the aromatic materials, ion exchange materials we made, used that same epoxy monomer. And with an epoxy monomer, the monomer itself adds 1 beta hydroxy group. So if you combine methyl diethanolamine with, for example, with an epoxy group, you'll get 3 beta hydroxy groups as a product. So this was our first column that had 3 beta hydroxy groups. And you can see now we're using a much more reasonable eluent concentration. Although I guess this slide doesn't tell you the exact concentration. Oh yeah, it does. So we're going as high as 35 millimolar hydroxide, but that's a whole lot less than the 170 millimolar we use with the AS5A. And as you can see, it's a similar list of organic acids. And part of the reason this is faster than the AS5A is because we're doing the separation at 2 mils a minute on this column, where the AS5A was done at 1 mil per minute. Yeah, one other thing I didn't mention about the AS5A was that was the first column, the first 5 micron column we used as a substrate was the AS5A. All right, next slide. And then in the same manner as was the case with the AS9HC, one of the problems with the AS11 is that the beginning eluent on the AS11 is, I think, 0.2 millimolar hydroxide. And as I was mentioning, the loading capacity of the system is partially a function of the eluent concentration. So that really low concentration eluent in the beginning made the peaks in the beginning pretty easily overloaded. And we overcame that by using the high capacity format of a super macroporous resin. But we used the exact same latex. I think it's maybe tweaked a little bit, but it's almost identical to the AS11 latex. And of course, the analysis is longer, both because the flow rate is not as high. It's only 1.5 mil a minute, and because it's a higher capacity column. But still, this column is, I think, the most popular column for organic acids of any column, even including columns developed later. It does have some weaknesses, which is why you see this solvent addition. For example, succinate and malate are not separated on it unless you add some methanol to the mobile phase. But in general, it has the best separation for organic acids. Next slide, please. Now, the AS15 column was developed as this was the first grafted column, the design specifically for separating organic, used with hydroxide eluents. And here we used a VBC monomer, and it's sort of the same idea as the AS10 column, where we were going for a high enough capacity so that it would work effectively with a hydroxide eluent under isocratic conditions. So here you see two different phases, the 5 micron column, the AS15 5 micron, and also a 9 micron column on the bottom, both using using grafting techniques to produce the stationary phase. They're slightly different selectivity, so the eluents aren't quite the same, but it's basically significantly faster separation to use the AS15 5 micron. But one of the things that consequences of using this high eluent concentration is as you move sulfate near chloride, well, that means carbonate is going to come out before chloride because it's always not that far away from sulfate. And so here you see the carbonate is actually right in between nitride and chloride. And so if you have a sample with a lot of carbonate, this is not a very good choice. But if you have a relatively modest amount of carbonate, this column will still be okay. And one of the things we used it for is rainwater analysis. It really works well for rainwater analysis. Next slide, please. Now, around the time when we, after we developed the AS11HC, the EPA started getting really focused on analysis of perchlorate, and they were using a method using the AS5 column with paracyanophenols eluent. And, I just felt like we needed a better solution, something that used hydroxide eluent instead of paracyanophenols. If you've ever used phenolic eluents, they are, well, they're usually not the highest purity chemical out there, although phenol is, but phenol you can't use as an eluent because it oxidizes under alkaline conditions. You need a para-substituted phenol. And the problem is most para-substituted phenols, which block the quinone formation process, are not very pure. But anyway, so we developed basically a low crosslink version of the AS11HC, and you can see the peak shape is a whole lot better when you use the AS16 for perchlorate versus the AS11 when you just used a simple hydroxide eluent. And that's because of because of the low crosslink. And one thing that you don't see in this chromatogram, but it's definitely a factor, is that you can't separate bromide and nitrate on the AS16 because of the low crosslink. So they basically co-elute. So if you wanted to do perchlorate and bromide and nitrate, the AS16 is not the column for you. Next slide, please. How did this get in here? It shouldn't be here. Sorry, my mistake. But anyway, let me talk about it a little bit. This was one of the, I take it back. Sorry, it's supposed to be here because they're in order, roughly. So this was the next thing we did after we introduced the AS16 was we wanted once again to target making an isocratic hydroxide column for common anion analysis. All the other hydroxide columns before then, except for the AS15, had targeted gradient applications. So here, instead of using grafting, we use super macroporous resin, and we use the latex approach. And one of the target applications, we wanted to be able to analyze organic acids that were of interest in analysis of high purity hydroxide. So we optimized the latex so that we could do a variety of different organic acids, and still it's not really compatible with isocratic conditions for things like phosphate. So we ended up using it mostly as a fast gradient column, or was optimized for organic acids, but a more limited set than you would see be of interest with like the AS11, but more focused on the separation of those early eluting peaks between chlorite and fluoride. Next slide, please. Now the AS18 was, see, we keep on going back to the same thing. I really felt like we needed to have an isocratic hydroxide column, so I started working on, and again, this came in part from a request from Japan. I can't remember exactly what the competitive thing was, but I started working on this kind of, as a personal project. A lot of the columns you've seen earlier, maybe I was involved in some of the early phases, but usually somebody else really developed the column. But really, in this case, I did the entire development myself. This is like the last column of the ones you're going to see that I did pretty much the whole development myself. And you can see here we actually do have phosphate and all the other ions separated under isocratic conditions. And again, if you want to do that, you have to have a relatively high ionic strength, because otherwise the retention time for the trivalent species will be too long. But here you can see it's possible to do under around 10 minutes the common anions. But again, carbonate is pretty close to chloride. So if you have a lot of carbonate, you're going to need a carbonate removal device to get rid of it, because it's otherwise going to interfere. Next slide, please. Now, the AS19 was, that old expression that necessity is the mother of invention. Well, when we developed the eluent generator, we had this one problem that we didn't really have any column that could separate bromate, chloride, chlorate, bromide, and nitrate with hydroxide eluent. Because all the phases we were using, like the AS9HC and the AS9, were acrylate based, and you can't use hydroxide eluent with them. Because they will degrade. They'll lose like 10% capacity a day or something like that in hydroxide. So I worked for 2 years trying to find an aromatic monomer that would work with this for this separation. and finally gave up on doing that. And I had worked on a project earlier to coat fused silica capillaries for CE using condensation polymers, and they were all aliphatic. So I was thinking if we could make a condensation polymer from a dialkyl halide, and I mean an alkyl compound with a halogen on each end, and then a diamine, you can make a condensation polymer that will have an ion exchange site in a regular pattern. But we needed to have beta hydroxy groups, as I was already showing you, to have good hydroxide selectivity. And the only diamine that's available with beta hydroxyl groups is ethylene diamine. You can buy with 4 beta hydroxyl groups on it, but it's very unreactive because the inductive effect of one quat makes the other one very unreactive, and it's already not very reactive because of all the beta hydroxy groups. So what I wanted was tetraethoxy propane diamine, and I went to our synthetic chemist, or one of them at the time, asking if he would make me some. And he said, well, maybe I could, but couldn't you just use an epoxy monomer instead? And I was thinking, yeah, I guess I could. So I started looking into it, and I found you could buy an epoxy monomer that had 2 epoxy groups. There are actually quite a few different ones like that, but there was only one that had good purity, so we bought that. And I started doing experiments with amine condensation reactions, and I found that they gelled readily. So I started working on a strategy for making a hyperbranch phase where you first make a linear polymer with a primary amine and this diepoxide, and then when you form it in the presence of resin, it makes a monolayer, but it has, for every nitrogen, still one, it's still a tertiary amine, so it will react with the epoxides again. And so if you just treat the resin with the diepoxide and then rinse away the excess diepoxide and treat it with amine, if it's a primary amine, then it will leave a pendant secondary amine group that will react with 2 diepoxides if you treat it a second time with diepoxide. And because of that fact that you have a doubling of the number of reactive ends with every reaction cycle, you can get a geometric increase in capacity by repeating the process over and over again. Most of the phases that I'm going to show you next use somewhere between 2 and 4 reaction cycles, but more where a reaction cycle is treatment with a diepoxide and treatment with amine. Some of them have a different amine for the last step, but a lot of them use just 2 reagents, the diepoxide and the amine of interest. All right, so the AS19 was the first column. Sorry, go back to the AS19. One more thing I wanted to say about it is that you notice that it has not only good separation of all the peaks and a very good peak shape, but chlorate for the first time is eluting before bromide instead of in between bromide and nitrate. And that's an indication of the fact that chlorate likes to interact with aromatic structures. And so since there aren't any, it has quite a bit earlier elution, and that's also true for bromate and chlorite. All right, next slide, please. Then around the same time, we the military was pushing back against the EPA on perchlorate because the primary polluter in the United States of perchlorate was the military, and they were arguing that perchlorate's not so bad for you, and one of the things they tried to do is to argue you can't use the AS16 because they found one waste site where the waste site was contaminated with perchlorate, but it also had parachlorobenzene sulfonate in it, and that erroneously resulted in a higher value for perchlorate than the actual value in this waste site, because the chlorobenzene sulfonate and perchlorate co-elute on the AS16. So I figured, based on the fact that there's no aromatics in this structure, that it would have a different retention time. And so we made a simple, I think this is a 3-cycle hyperbranch with just the same amine throughout. And as you can see, the parachlorobenzene sulfonate is roughly half the K prime of perchlorate on the S20 column on the lower chromatogram, whereas it has this identical K prime on the aromatic phase. So it ended up being incorporated in an EPA method as the validation column. So if you find perchlorate in that method, you're supposed to use the S20 to validate that it's really perchlorate and not something else. Next slide, please. Now, we also, around the same time, for the same reason, developed this column with the EPA, and it's actually specified in an EPA method. I forget the number of it, but this is designed with the idea of using it with a mass spec. So here they're using methylamine as the eluent because methylamine is very volatile. And they're able to detect very low levels of perchlorate using this method by direct injection. Next slide. And then the AS25 was developed in concert with a chemist at Phillips that was Phillips Conoco, that was interested in analyzing what he calls heat-stable salts and amine scrubber solutions. And the problem with all the hyperbranch phases before that was they couldn't separate sulfite from sulfate. And I must have worked on this off and on for at least 2 years, trying to find a hyperbranch phase that would separate them. And I finally figured out that you need to use a diamine to create a gap between the two ion exchange sites that's the precise distance you need to separate them. And after I did that, we had the AS25. You notice that the AS25 doesn't separate bromide and nitrate. There's actually an AS25A that does separate them by slightly changing the conditions. You can separate them. The peak shape for thiosulfate on the 25A isn't quite as good, but it's still okay. Next slide, please. And then we developed this phase, actually 2 different phases, not at the same time, but the AS24 and the AS26 were designed in concert to for 2-dimensional separations of organic acids, and oxyhalides, so that you could do really, I say oxyhalides, sorry, haloacetic acids, because there are 9 different haloacetic acids of a wide variety of different degrees of hydrophobicity. It's really hard to separate them all on an ion exchange material. I know Yan can attest to the difficulty of doing this. I think we've been working on trying to do this separation for 30 years until we finally got something that worked pretty well. But you'll see later we've made an even further improvement in this. But both of these are based on hyperbranched materials. Next slide, please. And then another interesting problem raised its head with regard to the analysis of oxyhalides is that the EPA method specifies that you're supposed to stabilize your sample with ethylene diamine. I think most people don't actually do that because they don't really need to, but because the EPA specifies it, in some places, such as in Japan, they are always adding ethylene diamine. And the problem with ethylene diamine is it forms a carbamate. I mean, ethylene diamine shouldn't show up in the chromatogram, and it doesn't. But the ethylene diamine carbamate does, and it shows up as that peak that's labeled ethylene diamine carbamate, peak 1. And it interferes with the determination of chlorite and chlorate, and therefore we developed a new version of the AS19 that has a better separation of the carbamate from the early eluting peaks. On the AS19, it really comes out in a bad place. So we designed it just to improve that part of the separation. Next slide, please. And then we later designed the AS30 to further improve that separation. So here you can see a really nice separation of the carbamate from the fluoride. And it's a little bit longer retention time, but it has, I think, the highest capacity of any of the columns you're going to see today for anions. So it can really handle high sample loads and still give good separations. Next slide, please. Then there was this column was designed kind of as a replacement for the AS17 with the idea of, optimizing the separation of glycolate and acetate and formate, and which are of interest in hydroxide production. And you can see a really nice separation of those peaks with the elution order. That's a little different than you would normally see. Most of the hyperbranch phases, glycolate and acetate co-elute. Next slide. And then the AS929 is a really interesting phase that we developed in conjunction with Professor Hatch. This one uses the sulfonamide ion exchange site that's designed so that the sulfonamide becomes ionized if the pH is high enough, and at lower pHs, it's just a polar substituent on the quaternary site. But because of the sulfonamide presence in this phase, it's kind of like a built-in buffer, and therefore it's more tolerant of extremes in sample pH than any other column we have. And so you can see in this separation a comparison with high ionic strength, where there's really no effect of the high ionic strength on the separation, where there's 1,000 ppm chloride and sulfate. Next slide, please. I think we're getting near the end here. And there's the AS31, which this is like a version of the AS24, but it was, again, using hyperbranch, but it was optimized for mass spectrometry applications. So the separation isn't quite as good, but some critical co-elution problems were solved with this one. Like there was a problem on the 24 with nitrite and one of the organic of the halo acetic acids, which we also fixed with this phase. So for mass spec, this is probably the best option for halo acetic acids. I think there's one last slide for anions. Yeah, this is the AS32. This is by far the most hydrophilic phase we've ever made for anions. Now you see we're eluting things like dyes and naphthalene trisulfonic acid peak 6 that normally are really difficult to elute without any organic solvent. And in fact, we're able to separate things like persulfate, which I actually thought, I used to think, well, it must be decomposing on the column because we would never see it. But in reality, it's just a really hydrophobic divalent, so it's hard to elute. But on this phase, you can quantitate persulfate in aqueous samples. All right, next slide. So we're going to quickly, because we're a little behind schedule, try to cover the cation columns. Next slide, please. When we first started doing ion chromatography, the columns for cation we're just using the surface sulfonated resin as the cation exchange site. But the problem with surface sulfonation is you have a cross-link gradient, because as the surface swells in water, the part that's at the boundary between the unsulfonated resin and the sulfonated resin, it can't swell as much as the part that's far away from it. And so you end up with a crosslink gradient, which puts the highest crosslink the farthest away from the surface, which is the worst place for the high crosslink to be if it's going to be a gradient. So we decided pretty early we wanted to make a latex, and the PCX 100 wasn't the first version. The first version was the CS3 column, but the PCX 100 uses a similar sulfonated latex. Took us quite a while to figure out how to sulfonate latex, but you can see one thing I should have mentioned is in the early days, the way you did chromatography of cations was you used hydrochloric acid for the monovalent cations, and you use ethylene diamine for the divalent cations. But the problem is with that eluent, it oxidizes to form this black goo that slowly turns your column black. And furthermore, it was hard to get off the column, so you really had to have one column for monovalence and one column for divalence. So the CS3 and the PCX 100 were kind of the first ones where you could do it without that. In this case, we used HCl and diaminopropionic acid, but still you can see the monovalents are barely separated, and the calcium and magnesium are miles apart from the monovalents. So the CS10 was the first column where the resolution was good enough you could really do mono and divalents with just an isocratic eluent. But we had a competition from Europe, from a group of Professor Schomburg in Germany, developed the carboxylate phase that was actually better than this. So next slide, please. So we started working on making carboxylated phases. Like the first column we made was the CS12 column, which I mentioned before. I don't have a chromatogram of it, but later we developed another one that was a little better for amines, which you see here, the CS14. This is a grafted phase on high surface area resin, kind of like the AS14. And you can see respectable chromatography, but still we had to add some solvent to the mobile phase. Next slide, please. And then the CS14 was the first phase that I developed where I'd say I finally figured out how to do grafting to get good efficiency, because one of the problems with the CS14 is we grafted in organic solvent, and I realized later that you're better off using a non-swelling solvent for the grafting. And so you can see the peak shape is pretty darn good for all of the cations. Maybe barium's the only one that's not really Gaussian. And for the first time, you could do really all the important mono and divalent cations in one run with all the way out to barium. Like doing barium on those previous columns I just showed would have been really, I mean, the CS a 10, for example, would be really difficult because it had such a high affinity for styrenic monomers. Next slide, please. Then we developed the CS15 specifically for doing trace ammonia. For some reason in Japan, they were really worried about ammonia in their drinking water. And it's hard to detect ammonia in drinking water when ammonia elutes close to sodium. And one of the problems with carboxylate phases compared to sulfonates is that the ammonia and the sodium tend to be very close to one another, usually just barely resolved. So one solution that we came up with was by essentially taking CS12A and grafting a crown ether on top of the first graft to add some additional retention for ammonia, even though the crown ether really binds potassium pretty strongly. It has a weak complexing ability with ammonia, which is enough to make a pretty good separation of ammonia from sodium. So we're able to do, I think, I don't know, like 1,000 to 1 ratio of sodium to ammonia on this column, maybe 2,000 to 1. Next slide, please. But then Maria Ray, who was the chief developer of most of these cation columns, developed a CS16 column to target the same kind of thing, but in this case, get the better sodium to ammonia separation by really raising the capacity of the column. And you can see the lower chromatogram where she's using an eluent that moves this potassium in between calcium and magnesium, gives you a pretty good separation of sodium and ammonia without using the crown ether, which required solvent in the mobile phase, which we later decided wasn't the greatest idea for suppressor life. So and this column is, one of the most popular columns, although I'd say the cation column that's most popular still is the CS12A. Next slide, please. Then we developed a series of columns targeting gradient applications, the CS17. That's for separation of biogenic amines, and you can see some of them here. And then next slide, please, shows the CS18, which was optimized for more polar amines, like the ethanol amines shown here. The CS18 is only available in 2 millimeter, in case you're interested in this one, but it's a pretty good one if you're interested in ethanol amines or highly hydroxylated amines. Next slide. And then we developed the CS19. This is the first and only column that we developed for cations using the super macroporous resin platform. It's grafted with a carboxylate phase, but you can see it has pretty good peak shape, and it can also do the ethanol amines, although the separation isn't quite as good as the 18. So that's another option. This one's available in both 2 and 4 millimeter. Next slide, which I think is the last slide. And then more recently, we developed the CS20, which is a version of the column that uses, it's the first column we designed that uses 3 different types of cation exchange sites. It has the CS12A actually has some phosphonate and carboxylates, but this one has sulfonates, phosphonates, and carboxylates. And because, as I mentioned, you get better separation of ammonia from sodium on sulfonates, we wanted a phase that has sulfonates in it, but it's diluted with these other 2 monomers so that they're not too close together, because if you have them too close together, then you have too much retention for calcium and magnesium. And you can see here we're able to do a separation where the top concentration is only 50 millimolar MSA. We can still elute the calcium and magnesium. But basically, most amines are eluting this middle window, so that the target of this column is to use it for gradient applications for organic acids, amines, and which is why the separation is set up the way it is. And I think that's the last slide. So you want to check to make sure, see what happens if you go, or maybe you're at the end, yeah. All right, so I guess now, sorry that ran over, but I guess we're open for questions if you have any.
There are some limitations on who can actually participate in the chat because you have to have a Microsoft Teams account in order to type the question. So now you have the ability to unmute yourself, guys, and ask the question with your voice, please.
Well, Alex, there's a few in the chat. Do you want to read them to Chris? Or
yeah, go ahead if you can do that, Brian.
Okay, so Chris, one question was when you were talking about the AS11 column, can we use the AS11 column for cyanide detection? I think they mean inorganic cyanide or CN.
Yes, you can. The thing that you always have to keep in mind when you're doing cyanide is that if the sample contains any metals, if a previous sample contained any metals, then they can form complexes with the cyanide in the subsequent injection of cyanide. So I think the the AS11, the cation exchange capacity isn't ideal because if your samples contain any metals, but otherwise you can definitely use it for that purpose.
Okay, there was another question. It's from an unknown user. It says, what causes the gradient hump that is commonly seen near the sulfate retention time? I've seen these with different columns and different hydroxide gradients. And at the end of the chat, I think the same unknown user posted a chromatogram. And if I look at the chromatogram, it looks like it's PFOS with, well, the title's PFOS with UV sulfate in there, but there's a big hump that comes out by sulfur sulfate. I don't know if you can see that, Chris, but that could be pollution or some kind of PFOS material that's not being separated very well. But in any case, that's, I don't know if you can see the chromatogram itself, but it is in the chat.
I can see it. Yeah, well, the basic situation when it comes to that hump is if you think about it, if the eluent contains any carbonate, because the retention time is in the beginning of the gradient, the K prime is really high because it's very sensitive to concentration. Any trace carbonate that might be present in the mobile phase accumulates, but because it's started accumulating at different times, it makes a broad peak, rather than a narrow peak. So it's really just all carbonate. If you use a carbonate removal device after the separation, you'll see that most of that hump goes away.
Alrighty. Another question is, what's the best column for perchlorate detection at detection limit of 1 ppb?
I think that depends a little bit on the sample matrix. I've heard some people say the AS16 is the best option when you have, especially when you have a lot of calcium and magnesium, and I'm not sure exactly why that would be so, but I mean, why calcium and magnesium would matter, but so for hard water, I think you're better off with the 16. I think if you have a less challenging matrix, though, the AS20 is probably better because it has less chance of interferences from aromatic impurities.
Good. Alrighty. Moving on, is the AS11HC suitable for testing reagent grade acetonitrile diluted with 10x with water? So 10x dilution of water, acetonitrile.
Yeah, it should work fine for that. In fact, of course, the thing you need to remember about acetonitrile is acetonitrile hydrolyzes in base, but the hydrolysis is not super fast, but it makes ammonium hydroxide. I mean, it makes ammonium acetate that in base will give you some ammonia and some sodium acetate. But it's not super fast reaction, so you can even inject higher concentrations than that with no problem on the S11 8C.
Okay. Are there any common problems with the CS17 column quantifying polyvalent amines, such as orientation of polyvalent means or charge of the polyvalent amines?
Well, if they are aromatic polyvalent amines, then they might be more difficult to elute, like drugs or something like that, where they have more than one amine. But the general rule is that they become more difficult to elute if the number of amines, as the number of amines increases. So, like if you take, I think the most amine groups in the chromatogram I showed earlier was 4 amines. But if you have like 6 or 7, it's challenging to elute them. And likewise, if you try to inject, you try to analyze ethylene diamine, polyethylene imine, you will find that, well, first off, it's a really complicated mixture. And secondly, a lot of them, the molecular weight's too high, and so you can't elute them. So you tend to see kind of a lump, not peaks, when you inject polyethylene amine.
Do you have a recommended hydroxide eluent column for the placement of the Ag14 carbonate column? We've seen issues with good baseline resolution when testing activated charcoal.
Well, if they're using the AS14, I would say they should. I think they would probably be better off trying to use the the AS22 because I'm assuming what's the problem with the activated charcoal is organics that are absorbing onto the phase, and since the hyperbranch materials are less hydrophobic, they probably will stay clean longer.
Okay. What suggestions do you have to reduce peak tailing of lactic acid using an AS11 column?
Well, peak tailing of lactic acid is a suppressor-related phenomenon, not a column-related phenomenon generally. So if you are using, I'm not sure what suppressors are currently available, so I may be misspeaking here, but you used to be able to buy a version that had green in it, and if you have that version, the peak shape will be better for lactic acid than the version that has resin, because the resin version is essentially an ion exclusion phase, and so it adds some tailing due to the permeation into the resin that doesn't happen in the screen version. Otherwise, generally you get better peak shape if you inject less, but if it's suppressor related, you can also improve the peak shape by reducing the flow rate, because the problem in the suppressor is related to the mass transport being slow in the resin in the suppressor. So if you cut the flow rate in half, it'll probably look better if you can live with the longer analysis time.
Does that also apply to the AS11HC? Would the high capacity version help, or adding
Yeah,
methanol help?
it's the same thing with both of them. Yeah, I guess you probably said the AS11HC and I was talking about the AS11, but yeah,
No, I
it's the
said
same.
the AS11. That's the question. I was just
Oh.
adding the HC to it, if that helps or not.
Yeah, right. That's actually applies to both of them. Yeah.
Okay.
But one thing I get with the AS11, I maybe misspoke a little bit about is that, as I mentioned, it's pretty low capacity. So, and since lactic acid is in that front, then one way to improve the peak, it could be causing tailing due to overload, and in that case, you should try cutting the injection volume in half and see if that helps.
Okay. Alex, is our hard stop at 1:30? Because we have a few more questions here. Do you want me to keep asking them, or do we
Yes,
want
please.
to wrap things? Okay, keep asking. Alrighty. What's the best column for low levels of nitrite in pharmaceutical excipients or excipients?
Well, I would say, you get the best peak shape for nitrite on the hyperbranch phases. So what I would probably do is use I'd probably use the AS19 for that.
Right. Thank you for the feedback on your cyanide question. Do you have any recommendation for quantifying cyanide and address complexiation? Chris, the only thing I want to add is that from your perspective here, we've been talking about conductivity detection and not talking about electrical chemical detection. Do you think inorganic cyanide gives a good response to CD? Just to kind of follow up on this question.
Yeah, I mean, well, first let me answer that, the follow-up first, and then I'll go back to the original question. Cyanide does create a signal, but it's a very weak signal because it's a very weak acid. So it's a weaker acid than carbonate, but you can see a signal, but usually in environmental applications, you'd want to use an electrochemical detector because signals, you're usually trying to do trace analysis by IC standards, and so you can't really do that by conductivity. But there are a couple different things you can do about cyanide and metals. One is the CS, I mean, the AS7 actually is, or the, like the two columns that I think we get the best results on are either the AS7 or the AS15. The AS15 has the advantage that it doesn't have any sulfonate sites. So it's really not going to be, concentrating metals like any other one. But the AS7 is often used in conjunction with, it both has kind of optimized sulfonation so that it's gives better peak shape for cations, which makes them easier to remove from the column. But often with with electrochemical detection, you add a chelating agent to the mobile phase to help minimize the metal problem. Like ethylene diamine, I think sometimes they add, I can't remember the other ones, but so I think what I would probably start with is the AS15 because it doesn't have any cation exchange site. Because usually adding the chelator causes some electrochemistry problems. So you get, because the amine can also be oxidized electrochemically. So your best option is to use a phase that doesn't have any cation exchange sites like this, the AS15.
Very good. I think we actually have an application note on that. AS15 for cyanide detection, if I remember.
Yeah, and that's the reason
remember
why.
correctly.
Yeah, I think if I remember right, if a lot of times people want to do cyanide and sulfide at the same time, and sulfide, I think, behaves better on the AS7. But if you're just doing cyanide, I think the AS15 is a better choice.
Ready? Alex, we're almost at time at 1:30. Do you want me to keep going, or? I can't hear Alex. Alex, you're mute. You're on mute.
Yeah, he nodded his head, so.
Oh, okay.
Yes, please go until all the questions are answered.
Okay. Let's see. We are using an AS22 column, and academic adipic and succinate and glutarate are very close to each other. And sometimes one sample shows succinate and other samples show adipic. Medium is, I guess that's 75% isopropyl alcohol and 25% water. Same thing with acetate, formate, and MSA, sometimes overlapping on each other. Is AS11 better than AS22?
Yeah, as long as you don't have, I was just working with some people at Merck on doing, picking the best column for the widest variety of organic acids that are in pharmaceutical applications. And I think what they found was if you don't care about, if you're not having a problem with succinate and malic acid coeluting, which don't coelute on the 22 or the AS11, or AS19, but for the other kind of medium chain length dicarboxylic acids, the AS11HC gives better separation. So I think that would probably be the best choice.
Yes, I think that's really much our go-to column, the AS11 or the AS11HC for most of these organic acids. I don't think the AS22 is really set up for that. But
yeah,
that would be the best approach, I think. So yes. What would cause linear diamines to produce an extra peak using a CS17 column in fermentation broth as the matrix? Is this incompatible? Column affinity issues.
So linear diamines. there are a couple of different things that could be caused by, if you're doing a gradient, if there's ammonia in the environment, you can get an ammonia artifact, just like you can have a carbonate artifact. There could be some impurities. So, you know, if you're doing gradients with cations, you really should be using the cation trap column in line. I think a lot of people don't recommend it because they don't really realize it. I mean, it's not as big of a problem as carbonate is in hydroxide, but I know sometimes you can be in a place where there's somebody in the lab is using ammonia as a reagent for something, and then the whole lab has ammonia in it. You don't really notice it, but there's enough that you get an artifact in your baseline just because somebody else in the lab is using ammonia. But the other possibility is if they're using a solvent gradient, sometimes there can be an artifact from the solvent. I don't know if they're using solvent or not. So I'm kind of guessing based on limited information.
Right. Do you think a CS19 would do any better, or what's your view on that versus a CS17 or any of our other alkylamine columns? Like the CS20, CS21, would any of those be any more help?
You know, I think the CS17 is still probably the best one, but you know, if they're long chain diamines, the problem might be that you have, you know, start needing to add solvent. So I don't know if they're adding solvent or not, but if it's hydrophobic enough, you will start to have problems if you don't add some solvent.
Okay. One individual is interested in knowing where they can purchase your book.
I think the book is available on Amazon if you want to purchase it there, but trying to remember who published it. I think it might be Wiley, but
Yeah, it looks
yeah.
like Alex gave a link to Amazon for the book. Alrighty. Would running a dilute 19% aqua ammonia NH4OH on AS18 columns for chloride and nitrate analysis cause interferences or damage the column? How diluted would the 19% aqua ammonia need to be?
Well, it won't damage the column, that's for sure. And how much, you know, when it comes to injections, it's always a combination of what's the concentration and what's the injection volume. So if you wanted to avoid dilution for example, because you're worried about evaporation or something, you can just reduce the injection volume. Of course, in reducing the injection volume will compromise your ability to do the lowest concentration. So I would think you can inject a pretty high concentration, but I don't know that you can. You might have some problems if you really inject it neat, because the suppressor has a limit for what it can tolerate as well. But I'm pretty sure you can inject a 10% solution of that without any effects on the chromatography.
Yes, normally we suggest a dilution to help out with that. So unless they're opposed to that, then I guess what you're saying might be an option. Go to a 10 microliter injection or 5 microliter, but there are pros and cons to doing that.
Like
Okay.
I know sometimes when people have some reason, like for carbohydrate analysis, where they don't want to do dilutions, and then we were recommending like the smallest loop you can make, or there's even some valve that allows you to inject even less than a microliter if you want.
Okay. Let's see, moving on. We are running amines for methoxypropylamine MOPA, and morpholine, and they co-elute. Do you have a recommended column for separation? We are using CS19.
That's an interesting question. I would say I would be surprised if they co-eluted on the CS20, if they co-eluted on the CS19, because of the aromatic monomer in there is gonna change the selectivity. So that's what I would probably try. It's the biggest difference from the CS19.
Okay, CS20 for that then. I have the following. Can they use together? AS18 column, CRD 300, ADRS 600, both 4 millimeters. On the Fisher website, it says Dionix CRD 300 can be installed in any Dionix IC system running carbonate as an eluent with a Dionix AERS 500 suppressor. I am wondering if I need to get a new suppressor. So, Chris, I think we're combining things here in that we have a carbonate removal device 300, which is for carbonate eluents, and yet they're using an AS18 column. Normally, we would do the CRD 200 for the AS18 columns, but you can go ahead and expand on that if you like.
Yeah, I guess the way to look at it is the 300 requires more surface area for the membrane to remove a lot more carbonate. So you're really better off using the 200 if it's a hydroxide column, because all it has to remove is the carbonate from the carbonate peak, which is a lot less work. So chemically anyway. So that's probably what I would do. But when it comes to the suppressor, the in theory, it shouldn't matter. The only thing is that, as I was saying about resin-based suppressors, they do behave a little bit like an ion exclusion column, and because of that, they will give a wider carbonate peak than you would get on a screen-based suppressor. But generally, I wouldn't worry about that part. It will be a little bit worse. One other thing I would add, though, is I guess if you're using a CRD, you don't have to worry about this. But another thing you can do if it's just a hydroxide column is work in the external water mode instead of the recycle mode, because the peak shape for carbonate is partially influenced by carbonate diffusing back across the membrane on its way in through the suppressor in the recycle mode. So you actually will see it tails more in the recycle mode than in the external water mode. But of course, if you're doing using a CRD, you don't really need to worry about that because you're removing the carbonate a different way. So that's just
Right.
another
So
option.
I think we have some things that are overlapping here on this question. So you have an hydroxide column. You wouldn't use a carbonate eluent for the AS18 if that's kind of in the question there, because that AS18 is a hydroxide column. The ADR 600 is our anion suppressor that we typically use in auto recycle mode. And then the question has the AUS 500 suppressor, which we have that in a carbonate specific suppressor configuration, and we have that as an external water suppressor. So I'm just trying to add a little bit of
I missed that part.
clarification here.
Yeah,
to the question.
yeah. Well, yeah, they shouldn't be, unless you're using carbonate with AS18, which I'm not sure why they would be doing that. They shouldn't be. They have no reason to use a carbonate suppressor or a CRD 300, because both of those are for carbonate eluent.
Right. Okay. Very good. Do you have a suggestion for a good screening column for a large number of anions and organic acids? I use the S11HC, but there are many new competing columns out there.
Well, I might not. I kind of feel like the AS19 might be a better screening column than the AS11HC, even though the workhorse is still probably AS11HC because it is a less hydrophobic phase but can resolve many of the same organic acids. It's probably a better general purpose screening column if you really don't know what you're going to be seeing in a sample. Whereas the AS11HC is part of its power is the ability to resolve a lot of different organic acids in the same sample, but in screening, you don't necessarily have all of the organic acids. You're just looking for one thing or another.
Yes,
So-
normally the HC we say is our whammogram because of the mono, di, and trivalent organic acids that you can elute out on that column versus AS19. But yes, I think that AS19 is a good recommendation.
Yeah, because you might especially if you're talking about in a pharmaceutical company, there might be, they often have the counter ion might be a wide variety of different anions for a basic drug, but they don't typically have all of them mixed together. So you don't really need to be able to separate all of them at the same time. But even so, at least at Merck, when they did a comparison between the AS19 and the AS11HC, they found that there were fewer co-elutions of they got a vote from the chemist in the team of what are the most important anions, and then they tried separating all of them on one column, and the AS11HC one as being able to resolve the most anions with no optimization of the gradient.
Alrighty. We have an AS22 for chloride, sulfate, nitrate, and nitrite. We had an issue last month of the peaks shifting quite a bit and needed many rinses to fix. The column was only in there for 2 months. We ended up changing the column. Do you have any suggestions as to why that may have happened?
Well, usually, I could, let me start with the basic thing is that usually if you have a loss of retention and the retention comes back again, that it either has something to do with your eluent or it has something to do with your sample. Of course, if I've done it myself one time, I remember distinctly as I put in the eluent in the bottle and I forgot to mix it up. And so it was a different concentration coming out in the beginning than at the end, which caused that to happen. Like in the beginning, the most concentrated part was in the bottom of the bottle. So the retention time slowly shifted until I shook it up. But normally the cause of that problem is a sample. That some sample that was injected contained a highly retained ion that never eluted, so you didn't really know about it, but it affected the capacity of the column. And then it slowly eluted at a low enough amount that it didn't really affect the baseline. So if that's just a guess, but that's the most likely thing from the symptoms. So if you see that again, what I would do is run a really concentrated eluent over the column so that it will remove it faster. And if you have any idea of what it might be, you can treat the sample beforehand. Like if it's hydrophobic, use like a on-guard RP, or if you know something more about it, that might be some polymer. I would start with an on-guard RP if I knew it was hydrophobic, though. So that's just
Right.
a thought.
Sometimes we suggest the on-guard H if you don't know what transition metals you might have in the sample as well, but the RP would remove the organics.
Yeah, the thing is, although there are some exceptions, but generally, if you get metals in your column, it doesn't affect retention time, although it might affect recovery or things like that. If the anions you're looking at might form a complex with the metals. But anyway, that's just my inclination is to suspect it's a sample anyway.
Okay. I need a robust column for the separation of glycolate, acetate, formate, chloride, nitrate, sulfate, and phosphate. The best I found is AS15, but it limits the detection due to the need to reduce the ppm levels to get the separation in the early anions. Any suggestion?
So the early, it was glycolate, acetate. What were
It was,
the?
yeah, it's pretty much the fast eluting organic acids. So glycolate, acetate, and formate, and then chloride, nitrate, sulfate, and phosphate.
Yeah, I
And
would
they're
say
using the
probably.
AS15 column.
Yeah, I would say the AS28 can do that separation actually better than the AS15 anyway, and peak shape is better too. So that's what I would use.
Right, okay. There are peak overlap coelution of bromide and sulfate ions using the AS18 column and KOH eluent of 23 to 45 millimolar gradient, flow rate 1 mil per minute, column temperature 30 C. Do you have any suggestions on how to resolve these two ions?
Well, it depends on which one is eluting first. If sulfate is eluting first, then what you want to do is raise the concentration a little bit in the region where it's eluting. Either start with a slightly higher concentration or make the ramp steeper, one or the other. If bromide is coming out before sulfate, then you want to do the opposite. You want to decrease the concentration or decrease the slope in that part of the chromatogram.
Would you try a step gradient instead of just this gradient linear grade from 23 to 45?
Well, yeah, that would work if you're, if you're willing to kind of redesign your separation completely. But if you just want to tweak it, that's what I would do. Now, one other thing that I've noticed on the AS18 is that, that separation is pretty temperature dependent as well. So if you sulfate and bromide have opposite effects with temperature. So if you raise the temperature, the retention time will get shorter for bromide and longer for sulfate. So if you just raise the temperature to 35, assuming sulfate's coming out last, that will help the separation. If sulfate is coming out first, you want to lower the temperature. If you have a column compartment where you can lower the temperature, if you set it to 25, it'll also probably tweak it the way you want it.
Okay. Let's see, we have two more questions if no more come in. What is a normal life expectancy for a column? Our cation column CS12A only lasts a max 2 months. Anion columns a little longer.
Well, the life expectancy of columns depends kind of on what the chemistry is, but like for the CS12A, the chemistry of the column is stable indefinitely. I mean, if you just running the eluent we recommend on the column a year from now or 2 years from now, it'll look exactly the same. So if it's shorter than that, it's almost always sample related. So then you have to, then what you probably want to do is look at what might be in the sample that's binding to the cation exchange sites and compromising the separation. For anion columns, some phases have shorter life than others, but all of them should last. I mean, any column, IC column should last at least 6 months, and often they last a lot longer than that. So if you really are only seeing 2 or 3 months, there's a serious problem somewhere in the system. I assume this is not capillary scale, but scale can also have some influence.
Yeah, no, they
on
followed up with 2 millimeter versus 4 millimeter. So microbore versus standard bore.
Yeah, okay. So there is a small effect of column life on diameter that's related to some impurities in the peak. So you typically get longer life in 4 millimeter than in 2 millimeter for anions. The effect doesn't happen on cations, so that's only a anion problem. But so that really short life on the CS12A is really puzzling to me, because the only thing that can damage that column, or I mean change it, is hydroxide. So I guess if you were injecting a lot of alkaline samples, it might hydrolyze one of the substituents in the polymer that's base sensitive, but it's not acid sensitive. So it really should be stable and definitely in acid. But anyway, I guess the point is, my main point is, it's sample related somehow. So I would want to know more about the sample before I gave you a good answer on that.
Right, right. I agree. We are getting a split peak on sulfate that shows up after a few days to a couple of weeks. I'm wondering if it is a result of the polyacrylic acid iron complex in the samples. Their sample is power plant feed water. And they use the AS15 column. Or is there any other reason for the sulfate to start splitting? Chloride still has perfect peak shape. So are we getting coelution here? Sulfate, or some other?
Yeah, well, there's a couple of things that cause splitting that's unique to one peak, but the most common one is there's something you don't see with the detector that coelutes with the peak. So, for example, the thing I was mentioning before, if carbonate elutes near chloride and you inject a big slug of electrolyte, you will often see peak splitting for chloride because the carbonate moved underneath the chloride, and then there's a little carbonate dip on top of the peak. So that could be happening on the sulfate in the same way, but
Well, they mentioned that their sample is polyacrylic acid and iron complex in their samples.
yeah, well, the thing about that, this is an anion separation, right? So there's a few other things that can be going haywire, like if you're injecting polyacrylic acid, it's not going to elute quantitatively from the column because of its high equivalent weight. I mean, high valency when it's fully ionized in hydroxide. So it could be partially related to that, but and then if there's iron present, then I agree, there could be it could be related to that, because the thing is that iron oxides will bind sulfate. And in fact, I've seen, like if you contaminate a suppressor with iron, you start getting sulfate tailing. So what I would probably do is, if you start seeing that, is to treat the column with oxalic acid and then treat it with base to get rid of any iron oxide, to see if it gets rid of the peak splitting. And it might be, well, if you can do it, I would try to get rid of the iron. I know that in some drinking water samples, they add iron as a flocculant inducer. And so sometimes you get problems that are with peak shape of phosphate and sulfate that are caused by the iron for similar reasons to what I just mentioned. But anyway, the point I was trying to make is that there's I think it's the CP1 or CP2 column that you can put on the line from the auto sampler that will strip out the iron. And so that it won't end up being injected on your column in the first place.
Right, that is. And I suppose you could do the UNGARD H or the UNGARD M if you wanted to take out transition metals or chelate it to some degree on sample prep side.
Yeah, the caveat though is that iron is it requires a pretty low pH to stay in solution. So a lot of times when the pH is above a certain point, it might actually be iron oxides. And then basically all of these things don't work very well with iron oxide. But iron oxide sticks to cation exchange resins. So it might be accumulating on the resin surface. But anyway, if that's happening, you can dissolve iron oxide with oxalic acid. So
Right.
So
Clean the
that
column.
yeah, you can still do in-column cleanup with oxalic acid. Just need to remember that the kinetics of that process are slow, so it's at least it's an hour or two treatment to remove most of it. I did experiments with suppressors contaminated with iron where you could see what was going on because we took it apart. And to get rid of all the iron really usually took overnight with oxalic acid. But you can get a lot of it out with like an hour to 2 hours.
Okay. Most of our sample contain organic amines for anion analysis, and it creates problems many times. How to get rid of that? How to get rid of the
Well,
organic amines, I guess, is the question for
yeah, I
anion
mean,
analysis.
there I would use an on-guard H, like that's going to be really efficient at removing the organic amines. And it won't affect your anion analysis unless you're trying to do nitrite, and then you should use the on-guard sodium. But the on-guard H will be more efficient at removing the amines than the sodium. So as long as you're not interested in nitrite, because the on-guard H has some influence on the recoveries for nitrite, so you're better off using the sodium in that case.
Okay. Follow up on the CS12A short life. The sample is basic pH between 12 and 13. We dilute the sample 100x. The main ions we are measuring are chloride and sulfate, and cations are potassium, sodium, and calcium.
Yeah, so it could be a pH problem. One thing you might want to consider, of course, I don't know from the description why you'd have such short anion life, but for the CS12A, if you're trying to do the cations, then well, I don't know. There's not really I'm not sure what's causing what is inducing the high pH, but if it was I guess you could just spike in some acid and neutralize it, because it's not going to show up in the cation chromatogram anyway. Like if you spiked in some hydrochloric acid, well, not hydrochloric acid, say MSA would be a good thing. You could drop the pH of the sample and then you'd probably get longer column life.
Right, so the CS12A column is our cation column, so that will see the potassium, sodium, and calcium, but your anions are going to fly through the column, so chloride and sulfate are not going to be retained.
Yeah, but what I'm thinking, see, that's what I'm thinking is at least for the cation, because if I remember right, he was reporting the shortest life on the CS12A.
Right.
So I'm thinking and that might be damaged by high pH samples. So what I would probably do is for that column, I would try spiking in some MSA to get the pH near 7, and then see if the column life is better. Because all you'd have to do is like inject 10 microliters of MSA or something, and it'd probably be plenty. But for anions, we need to know more about what that high pH is due to, because it might be something in that the base in question might be causing some other problems for the anion separation.
Alrighty, well, Chris, that's all the questions in chat. Alex, I think it's according to my clock, it's 2:03 my time, Pacific Coast time.
Yep. Thank you, Chris.
Okay. All right.
Thank you, Alexandra. Thank you, Brian. I will put this recording on the YouTube, and I will send to the author and also to all the attendees the link to that.
Okay.
Hope to see you again. Cheers, Chris.
All right. Okay.
Cheers,
Thank you,
y'all.
Chris. Thank you for your contribution. It was greatly
Okay.
appreciated.
Bye. Cheers, y'all.